Anyway, all right, so again, I hope all this is kind of useful. I am going to, if I have, I probably don't have time today, but I'm going to go over some general, like, here's things every physical chemist should know. Maybe today, probably not, maybe next time. There's a lot of little factoids you should remember in your head, like what is KT at room temperature in every unit possible. That's something you should all actually know. Regardless, let me review a bit, like I'll always review, and then get into some new material that's hopefully kind of interesting. So recall that we had the statistical definition of entropy. Okay, and I'm using W for number of microstates. If you are going to do an analysis, and we're going to start doing analyses of systems, models, that we create the model by just somehow, and we will analyze them under some statistical paradigm. The statistical paradigm will depend on our definition of entropy. This is our definition of entropy. I will show you how to construct these models, but let's say you construct a model such that entropy, K, L, and W is your guide. That means that U and V are constant. Okay, so your model has to be constructed in such a way that U and V are constant. Now, if that's the case, okay, so let me show you how you would do that. One thing that is immediately apparent for constant U and V would be a molecular dynamics simulation. I actually wrote my own molecular dynamics simulation code when I was your age. It took me about, to do liquid argon, to do a molecular dynamics simulation of liquid argon took me about 3 days. Most of the code, and this was 20 years ago, there was still an internet, and I found most of the code on the internet. I just stitched it together. I translated it from Fortran to C. But anyway, so we're going to do molecular dynamics simulation for all the reasons that we do molecular dynamics. And it will be a box, so we have constant V figured out. It'll be filled with water and maybe a protein. And the water in the box will move. It will move according to Newton's equations of motion, which is that a force is the derivative of the potential. The potential is defined by some parameterization. You'd have Coulombic attraction. You'd have a Leonard-Jones parameter interaction. Anyway, the potential energy is well defined, minus the derivative is the force, and once you know the force, you can start moving things. Okay, that whatever. The neat thing about that is, I already said that V is constant. U is constant as well. If you solve Newton's equations correctly, these atoms are moving around such that the internal energy is 0. Okay, great. So my point being that if you do molecular dynamic simulations to the easiest way possible, it is automatically U and V are fixed. And that means that you're working with this statistical definition of entropy, and every configuration of water, and by configuration I mean like this picture. If I simulate it some time period in advance, the waters are in different places because they move. That's a configuration. Then I do that again, and that's a configuration. Each configuration has the same entropy. Each configuration is equally probable. Each one is as representative of water. Each configuration is as representative as water as any other. That means that the properties I'm calculating, whatever property they may be, I don't know, why are you doing the simulation? It means that that property can be averaged together with all the other properties measured from different configurations with equal weight. They're all equally probable. Again, I don't know what property you're measuring, but whatever that is, every snapshot, every configuration you make in your simulation is as good as any other because they have all the same entropy and they're all equally probable as a result. Okay, so anyway, so that's molecular dynamic simulations. Those are very good in this statistical regime, which we're going to give a name, microcanonical. Okay, that's called a microcanonical simulation. Okay, what do you do? Now let me give you an example of what is not so easy to analyze in the microcanonical. Let's take a 2-level system, and let's give it an energy splitting that we'll call epsilon. And let's put a particle in. Let's put two particles in there. One's in the ground state, so this will be 0, and this will have energy epsilon, and one's in the excited state. Okay, so this is our quantum mechanical system from which we will do statistical analyses. Fine, whatever. The problem is that the internal energy would be epsilon, because the total internal energy is 0 plus epsilon, because there's two particles, one with 0 internal energy and one with epsilon internal energy. The total internal energy is epsilon. So that I have this configuration, and I have only one other. Whatever properties I am trying to calculate from this have to be done from this plus that configuration. They both have the same internal energy, and it has to be held constant in the microcanonical. This has internal energy epsilon, and so does this one. There's only two of them. Well, that makes the calculation of averages of this system quite easy. However, it looks unsatisfying. What about a configuration composed of this? Or this? What about these configurations? Well, they cannot be averaged in. They have different internal energies. You cannot violate the constant internal energy. So if this is your system and you wish to analyze it in the microcanonical, great. You've got these two configurations, but you can't include those. That may not be a good average. So this does not look like a very good thing to analyze via the microcanonical. Okay, so instead, let's go to a different statistical regime. Let's go to, where am I at? Let's go to the canonical. And that is when we take entropy and we Legendre transform out its dependence on U, and instead put it on beta. Remember, Legendre transform, subtract the variable, the natural variable, times the conjugate. The conjugate of U is 1 over temperature, and so we're calling that beta. 1 over kBT is beta. We just call that 1 over T. So this is a canonical entropy where T will be constant. V is still constant too. Okay. So the canonical world has constant T and constant V. And that's because we're working with this Legendre transformed entropy, which, if you recall, we did a very short little derivation to show that's minus the Helmholtz energy. And that is also equal to the natural log of Q, where Q is the partition function. Q, now I did a little derivation, but if you don't remember it, that's fine, if I got videos. But Q is the sum of states of e to the minus beta. Now don't, just in case, I know some of you might not quite remember, that's fine. Maybe you're too shy. Beta is 1 over kT. 1 over beta, the internal energy. Okay. All right, now, microcanonical. Do your simulation such that internal energy is held constant. Canonical, what you want to do is define Q. Two very different routes to property analysis. Try to figure out how to do an analysis, try to figure out how to set up your simulations at constant U. This guy, what simulations? Just figure out Q. However you figure out Q. As I showed you last time, I'm going to show you a little bit more today, Q contains all the information of the system. Last time I showed you how you can calculate Helmholtz energy. Last time I showed you how to calculate the average internal energy. Maybe I'm being a little overwhelming, but here's the point. In the canonical, if you calculate your partition, the Q gets the special name partition function, you can do calculus on Q to extract all thermodynamic properties. It's very convenient. It's very easy to figure out what Q is because quantum mechanics often gives us the number of states and their energies. It's the natural result of solving the Schrödinger equation. This is generally everyone's friend. Sometimes, though, like when you're doing MD simulations, the microcanonical is your friend. Sometimes this is easier, sometimes this is easier. Most of the time this is easier, but sometimes this is. And let's see. As much as you just have to figure out Q, which you may be able to do on pen and paper, This one, you just simply have to set up configurations with constant internal energy, and if you're doing MD, that's actually shockingly easy. Okay, now, what do I want to say about this? All right, so let me give you an idea. In the canonical, let's talk about MD simulations. And you know we have software, UIC has licenses on software to do quantum mechanical calculations, to do molecular dynamics calculations. What is different about this? I used to be an MD guy, by the way, so, and I just told you I wrote my own programs. You just write the software, let it run. You're automatically going to hold U constant by solving Newton's equations of motions. In a canonical simulation, and U is held constant. T fluctuates. You cannot hold U constant and T constant at the same time. That's because they're conjugates. It's just impossible. In this case, you're going to hold T constant. Now, the way you do that is when you find that T is fluctuating, you're going to inject energy. Here's the pretty picture of that. You're going to inject heat into it. Let's say you're doing a simulation and you have ways of calculating the temperature, and the temperature is dropping. What you do is you heat it up. It's very easy. What you do is you scale the velocities. You make things move faster. Temperature is kinetic energy. You just make them move faster. It's really easy to do. And you get the temperature back up. If the temperature drops, you heat it back up. So that's how you do microcanonical MD simulations. It requires a little bit more programming that you don't have to do with a microcanonical. That's why it's easier to do microcanonical MD simulations and a little harder to do them in the canonical. You have to do some more programming to do this. It's not hard, but it is extra. Okay, there's MD simulation. Now what about this stupid problem? The two particles on a lattice of energy epsilon. Okay, now remember, all you have to do is figure out what Q is. And for various reasons that I'm actually not quite sure about, what it would be is we're going to just take two partition functions for each particle and multiply them. I forgot why that works. Okay, the first one is the sum of states. There's only two states, so there's only two members of the sum. And for particle 1, it's e to the minus beta 0, which is 1, plus e to the minus beta epsilon. So that's the first state and the second state on particle 1. That's this for particle 1. There's only two states. One has u of 0 and one has u of epsilon energy. Okay. Then ditto on the second one because they're basically the same thing. And what ends up being is that. Okay, what's good about this is now that I've got the canonical partition functions defined, using formulas that we'll chip away at, I can now determine all the thermodynamic properties of the system with that. There are a zillion, for every property I can think of, there is a formula with Q in it that gives me that property. I've defined everything in G. That was kind of easy, wasn't it? It was. And I'll actually do a little bit more with this in a minute. Anyway, microcanonical, canonical. Sometimes the canonical is your best friend. More often than not it is. But every now and then the microcanonical is your friend. Pick and choose whichever's easiest. They actually will always give the same answer. And again, I'll actually show you an example. They'll always give you the same answer. But one of them can take many steps and one of them can be done in 1 or 2 steps. And again, I'll actually show an example. Are we doing all right? Yeah? No questions? Okay. So that was actually kind of a review. And let me see, where were we at last time? In terms of, okay, again, the canonical is definitely almost universally the easiest one to work with. This weird Q thing, where's entropy? Where did entropy go? Nowhere. I have this partition function thing. I will get all my properties from the partition function. Where's entropy? Well, I don't care. It's gone. I don't need it anymore, and that's fine if I get my properties out. Now, last time I showed you that one manipulation of Q in the canonical is to take the derivative of the minus the derivative of the natural log with respect to beta. Okay. Now, remember, in Q's world, in the canonical world, temperature is held constant. That means that internal energy is not. You have to pick and choose. You cannot hold them both constant. Microcanonicals use constant, but not T. Canonical, temperature is constant, but not U. Again, I told you for every thermodynamic property, I have a formula with Q in it. That's U's. So now I can figure out the average U. There you go. I showed you this last time. It wasn't particularly difficult. Part of the derivation is for any average, this will always be true, that the probability of that state times the internal energy of that state, of all states, will be the average internal energy, or whatever property. And the probability happens to be e to the minus beta u over q, and this happened to be, of course. And again, I covered this last time, so I won't beat you up over it. Okay, tricks with the canonical. Now let me show you another one. And I alluded to this at the end of last time. And it gets you, physical chemists are not as mathematical as physicists, but you should have some decent level of ability in this regard, because you should. I'm trying to remember what the heck it is we're supposed to be doing. Okay. Now this is going to appear as a fishing expedition, but what I'm going to do is the double derivative of natural log of Q. Okay. Now, maybe some of you remember, I already told you what we're going to find, but anyway. Maybe you remember, maybe you don't, but anyway. Now, last time, as I just said now, the first derivative will give you minus the average internal energy. So now I'm solving this. Okay, so what? Okay, now with this guy here, let me write the derivative. Let me remind you what the average is. I'm going to write it slightly differently. And where did my sign? So it was kind of weird that like some of the states disappeared anyway. Maybe I made a slight mistake, but anyway, I'll just chart forward anyway. Okay. So again, this is I'm missing some of states. I'm missing something here. Yeah, I should have this. I should have some of states. Oh, sorry. I told you I try not to do that to erase over what I just wrote, but I just screwed up. So, oops. Okay, so there's this. Okay, now what do I want to do? I actually want to stare at this blank because I'm a little confused. Okay, no. What I want to do is a derivative. And maybe some of you are having some trouble. Can you see what I'm doing, or is this? Can you see what I'm? Anyway, here I'm going to just write. Okay. All right. So derivative with respect to beta. Let's see. First thing to write is the sum. Let's just assume that has some states. Let's. What I'm going to do is take this guy down. So if I, e to the ax derivative with respect to x just brings down an a. Looks like it's actually bringing down a minus. Beta is my guy, so I'm bringing down a minus u, minus. So I end up with the use of I squared. This times that, essentially what's going on. Minus, those have canceled. And what I'm left with is, but I'm still left with these things here. So I end up with this. Because the e to the minus beta u over q, sum thereof has not gone away. Okay. So this is clearly equal to the average of the square u. Okay, now I'm not done because this was the derivative of this, but remember that Q has a beta in it too. So I haven't done the first derivative properly. Okay, plus, let me see. Okay, again, I'm assuming you remember that this is sum of states, u sub I, and beta u sub I over Q. Okay. So now again, Q has a beta inside of it. What is the derivative of 1 over f of x with respect to x? Well, that's the derivative of f to the minus 1. That will be, bring down a minus sign, I've got f to the minus 2 times the derivative of the inside. Okay, so that means I've got a q squared on bottom. I brought down a minus sign, so that's been canceled. There's my plus. Sorry, I know I'm doing this kind of light and quick, but hopefully it's not too mind-numbing. Okay, now I've got to do the derivative of the inside, and I still got a sum. That's going to bring down the u sub I, and I'm going to pick up a minus sign. And the Q's still there. Okay, yeah, there we go. Now this ends up being average, yeah. No, I screwed up. Yeah, why would there be another Q? Why, yeah, that was stupid, sorry. Again, this is, sorry, I know I'm just doing this too fast. Okay, let me just back up. Derivative of beta, I acted on this guy first, that gives me this. But then, being the product rule, I didn't have to act on this guy because it hides a beta. The derivative of f to the minus 1 brings down the minus sign, f to the minus 2 times the derivative of the inside function, and that's the derivative of the inside function. What I can do is, and I already just ballyhooed about not doing this, if I partition each one of these a factor of q, I instantly see that I've got this. Okay, that's what I've got. And I will now write that over here. Now this is where it's coming off. So let me summarize. The derivative of natural log of the partition function with respect to beta. Those things to the right is the difference. Okay, there you go. What's this? Now what's this called? Statisticians should have had it in high school?
Variance.
The variance. Yes, it is the variance.
You should have had it in high school.
I don't know. Considering high school, I don't know. I don't quite remember whether I learned this in high school. I think, how did I learn this in high school, maybe? Of course, the square root of that is the sigma. Remember, sigma squared is variance. Sometimes I get confused what's what. They're really the same thing, basically. Okay. Well, that's it. What? Isn't that cool? No. Okay. Let's go further then. All right, now let's look at something else then. Let me remind myself. Okay. Well, so what? All right. Well, hold on. Let's go back to this. This is still the same problem. This is still the double derivative. Make sure I run that. Okay. So this ends up being. Now I know that the derivative with respect to beta. Let's not forget what that actually is. I'm just doing a little, what I've done is a substitution to the calculus. I've actually done a substitution of variables in the derivative. I'll show you how to do that in case your calc might be a little rusty. Okay, so this is what this is. Because beta is 1 over temperature, I'll show you how to manipulate this into this form. Your calc might be a little rusty to know how to do that, but regardless. Okay. I can show you how to do that. Now this guy, and I'll show you how to do this too, it happens to be minus kb t squared. So what's this? The change in U with respect to temperature. Remember, we're at constant volume. We covered this on day 1. No, we didn't. We did not cover this. I'm an idiot. I forget. It's one of those things I didn't cover because I didn't have time. heat capacity, constant volume. So what did I just find? I just found that the variance in internal energy of a system is equal to and I feel like I'm missing a minus sign somewhere. Anyway, I might have screwed up the minus sign somewhere, and it matters, but I'm too. No. There's the minus sign. Okay, there's the minus sign. It's right there. It's from the original copy. Okay, it's making it plus. Okay. Anyway, here's the point. Heat capacity, fluctuations in internal energy. Fluctuations in internal energy is responsible for the phenomenon of heat capacity. Remember, I told you we were actually going to discover this last time. So what happens is, and again, speaking as someone who spent way too long doing molecular dynamics simulations, I really like, if I was really a physical chemist, and I once was, obviously, I did molecular dynamics simulations, I would require my students to write code to at least do liquid argon, just so you have some idea how the heck this works. When you're looking at molecules interacting, and again, a molecular dynamics simulation is a great way to do it. The larger, remember we're in the canonical. I am injecting temperature, some energy, to keep the temperature constant, and U is fluctuating. That means that these molecules, water, right? So it's water, right? These guys are interacting. Of course they're interacting. This configuration is a happy one, right? I've got a nice hydrogen bond going. These two waters are digging each other, right? So they're married. This is a very good configuration. Sometimes they will not be. Thermal fluctuations cause them to move, and sometimes they will butt heads, and sometimes they're like dogs sniff each other's butt. So they're good, they're bad. It changes, it fluctuates with motion. Motion is entropy, right? It's moving around in a chaotic manner, which I'll call entropy, and that causes, in this case, the interaction to be good, sometimes it's bad. Okay, that's a child knows this. Sometimes the dogs get along, sometimes they fight, it's the same thing. What I'm telling you is that's why you have heat capacity. That's where that comes from. The ability to absorb heat and partition that into temperature, which is basically what heat capacity is, comes about by the fluctuation in molecules interacting with each other. Now, I don't know how the hell else you would know that. That's not intuitive to me at all. I don't know, heat capacity is heat capacity. Where's it come from? I don't know, it just is. Well, now I do know where it comes from. It comes from the fact that molecules fluctuate the way they interact with each other. That's where that comes from. And we only know it from statistical mechanics. So again, a relationship you could have never figured out on your own, or by any experiment for that matter, and we figured it out. Maybe, I don't know, maybe a molecular dynamics simulation could have figured it out. So there you go. I hope that was kind of neat. And I'm going to show you a couple more derivations with canonical and microcanonical. I think we'll only get one of them done with the time we have left. But again, so this is just an example of revealing relationships that could not be done any other way. Other times we are trying to be practical, and especially if you do, actually a couple of you join molecular dynamics groups, then you definitely need to know how to do this, because this is what you do with your life. I do want to point out to you, though, that, again, if you're in the physical division, you should not balk at this. This should not scare you. I normally like to see df of x with respect to x. Instead, I see df of x. What's the change in f of x with respect to 1 over x? Now that throws me off. So what the heck do you do? For one, you should know that constants can come out, and 1 over x is x. So this is what I actually have. Again, how do I take the derivative of x with respect to 1 over x? That's funky. Okay, an easy thing to do is to say that y 1 over t. And therefore, this is the derivative of 1 over y with respect to y, which is actually quite easy. That would be minus 1 over y squared. And then we substitute in what y is. Don't forget your kV. Y is 1 over t squared. Don't forget the minus. There you go. Anyway, that's where this came from. Just want to show you that. So again, your calc should be this good. So we do expect that. That's reasonable. Some other harder calculus things that you may not quite be so good at is solving differential equations, second order differential equations. That can be very tricky, which is of course what quantum physics is. Anyway, so there you go. Tell you what, more tricks with the canonical, more tricks with the microcanonical. And let's do something that is relevant to NMR. We're going to go back to that spin, those two-level spin. Really, two-level systems, there's really a lot of two-level systems. Ground state, excited state. Maybe there's more excited states, but let's not worry about them. NMR. NMR is a thing. I don't know if anyone's joining Oreo's group. One of the things that's causing us problems anyway. NMR, spin up, spin down. In the magnetic field, one's ground state and the other's excited state. So there's lots of two-level systems. Okay, and I'm going to draw what I already drew. It's just I'm going to add more particles. I'll just add as many. I'll add a few. Okay. Again, I've given the excited state energy epsilon, and that's the only state. Okay. Now, instead of 2 particles, I'll say that there are n particles. Okay, and m in excited. Okay. So again, I'm model building 2-level. Energy, I'm allowing n number of particles to be present in this system, and m in here and n minus m in the ground state, m in the excited state, m minus m in the ground state. Now I can already tell that these are bosons. If these were electrons, this would not be happening. Only one state, only one particle in a state. 2 if you include spin up, spin down, but I've allowed n, that makes these bosons. Hopefully you know what I'm talking about. You should. If not, you can Google it. So I can tell again that these are bosons. So this would actually be a very good model for NMR of protons. Protons are bosons. There can be multiple, many in a single state. Bosons can do that. Wait, did I get that right? Both. Fermions cannot. Fermions are electrons. They cannot do this. Bosons are protons, they can do this. Anyway, I'm just rambling. Okay, so here's a model that certainly is relevant for spin, for NMR, and probably some other things. I can do some tricks with this, I will. What I'm going to do is show to you some very fundamental ideas about populations and temperature. I'm also going to show you that negative temperature exists, but you can never achieve it. So that's kind of cool, right? Negative temperature. How could that be? Anyway, so I will show you how to create a system with negative temperature. Okay, the total internal energy will be the number in the excited state times the energy of the excited state. Okay, so that's easy. Okay, now we have to do some Googling and look up the signs of permutations to know what the total, we're going to do this in the microcanonical. Sorry, I should have said that. We're going to do this in the microcanonical. And to do that, I'm going to need to know what the number of states are. Okay, now that's going to be a function of the total number and the total number in the excited state. And again, I Google permutations because I forgot how to do this. And I find that in a 2-level system, this is the number of permutations. Okay, so anyway. Hopefully, I remember learning permutations in high school. I know that there's ways to figure out what the total number of ways to arrange n particles into 2 systems. It is this is the answer. So there you go. So now I've got the number of states. Now notice that if all the particles are in the ground state, then n is 0. And 0 factorial is what?
1.
Right, so this would be n factorial over n factorial, which is 1. Now, sure enough, there's only one way to have all the particles in the ground state. Right? There's two ways, no, that doesn't make any sense. Okay, let's say n particles were all in the excited state. That means m is n and n is n. So that would make this 0. That is n factorial, that's n factorial, it's still 1. Okay. All particles in the ground state, there's only one microstate. All particles in the excited state, there's only one state. So this is correct. Now remember, if m is 1, then there should be n ways of doing that, because each particle could be that one. I'm just trying to recalibrate you in case you're like totally forgetting about permutations and all that. So hopefully that's kind of stupid anyway. Okay, so I've got the number of microstates defined. That means I've got entropy defined. And of course I have to remember that I've divided, in all my microcanonical equations, I divided that by kV. Okay, so now I've got entropy defined, so that's great. Okay, now if n is large, what I'm going to want to do, and I will do this in every microcanonical simulation, is to use something called Stirling's approximation, which is that natural log of a large number. Natural log of a factorial. Natural log of the factorial of a very large number is this. Yeah, you've seen this before, right? Yeah. Okay, anyway, it's kind of neat. Once x gets to about 1,000, it's like perfect. Now, guess what x would be? Well, obviously we've got n, and n will be on the order of about, seriously, in an experiment, you're not working with about a mole. You're usually working with about a tenth of a mole in almost anything you do. So that's 10 to the 23, 10 to the 22 number of particles. When I'm handling my quantum dots, I'm usually handling around 10 to the minus 19, 10 to the 19 number of particles. Again, this is fine at about 1,000. It is basically impossible that in all of your experimental blah, blah, blahs, you are going to be looking at more than 1,000 unless you're a Jang's group, but forget about that. Anyway, so with that, I can, anyway, I'm gonna do some things with that. Here, let me, oh God, this is a nightmare. Okay, this is painful, by the way. Let me go ahead and use it. And I'm gonna be a little bit late. Maybe we won't quite finish this today because we're going to be out too much. Okay, natural log of a over b is natural log of a minus the natural log of b, so don't forget that. So there's the top part. Let's do the bottom part minus the natural log of b. That's what I'm doing now is the bottom part. Since it's minus, this last part ends up being plus. Okay, and then I've got, that was this part, then I got that part, so I've got still more to go. Minus m, ln m, minus is plus. Okay. Sorry, this goes on. Yeah, this is a little sucky. It is what it is. Just are meticulous and keep track, which again, in the physical regime, that kind of should be your personality. Hopefully, just keep track, right? All right, so what? Okay. It turns out that the change in S with respect to U is 1 over kBT. We've actually covered that a few times. And the internal energy, I've already written. I'm just going to write it again. Okay, that means that the derivative of all this, kb, derivative of, you see, I can define the temperature of this thing. again, remember, the whole point of this jazz is to set up a model for your system in the microcanonical, where there's no partition function. If we're doing canonical, we define partition functions. In the microcanonical, we have to define the number of states. So I've done that. And now I can start manipulating it to get thermodynamic properties. Here's the temperature. And there's other properties I can get too. So let's do temperature. You know what? This is questions.
Why is ds divided by kb?
In these derivations, it always
Because
everything is divided by kbt because let's do this. It comes from this. So all of the formulas I've been deriving have actually been from here. So notice that I defined this with that permutations, all the factorial and all that jazz. Therefore, it's S over KB. So wherever I write an S, I need to also remind myself to divide by KB. And also, don't forget this. We covered this on the first day. And therefore, ds. Now, again, because of the Boltzmann formula, we just always divide by KB throughout. And anybody's equal to natural log of microstate. So anyway, that's why we do that. So it's impossible for me to be doing anything with S and not dividing by KB. Because so basically, this guy tends to be easy to set up. For the problems I give you, it will be easy. Even if it ends up being 10 miles long, it's still definable. And then that gives me S over KB. And then I'm going to manipulate this to get to thermodynamic properties such as temperature. Anyway, so that's where that comes from. Okay, now we're kind of out of time, so I won't go further. But what we're going to be able to do is, why am I doing this? We're going to take the derivative of this, basically with respect to little m. That's our goal. When we do that, we're going to solve for temperature. And what you're going to find is that there is such a thing as negative temperature. That's the kind of cool thing. Which is like, it should be like, what? Negative temperature? Yeah. We can, and as much as this is a real system, and it's fairly representative. It's representative, again, of NMR. It's actually really quite accurate. This is absolutely certain, and there is a negative temperature. You can have negative temperatures, which is kind of mind-blowing. But then I'll show you that there's a weird reason why you can't actually have negative temperatures. So, and it has to do with the fact that you can't heat things up to infinity. Anyway, okay, you'll follow when we get to it. But anyway, I'm out of time, so I don't want to keep you anymore.